microcontroller boards might have some sensors already, but 8051 doesn't have any sensor, or even we don't have any sensor ADC chip. Okay, that can convert your values. That means what? Your ADC doesn't have all these things. We need to connect it externally. We need to connect ADC externally. Okay, so ADC is your analog to digital converter, which we are using to convert all external physical values to your digital, such that you can read values. Okay, because your microcontroller understands only digital things. Okay, so here it can be of various values. Now, examples might be like temperature sensor, humidity sensor, or you can say you have a fire alarm. Okay, anything. Oh no, fire alarm won't work, because I think it can be depending on what type of sensor it is. Either it is simply detecting smoke, or analyzing how much smoke is required to alarm a flag. It depends on that. Okay. Or you can say you're using in your bikes some sensors, odometer or something, right? So all these comes under your sensor. Sensors are nothing but input only, but they are used to detect external physical values. Okay, now here what happens is we need to convert that values, because your 8051 understands only and only numbers, right? So what we are doing is we are connecting external ADCs. Here also we will have some serial or parallel ADCs, but we will go for serial ADC. Okay, no, sorry, we will not go for serial ADC, we will go for parallel ADC. Why? Because serial ADC again will have something like one bit by bit output.
Yeah.
Okay, so we will go for parallel ADC. The parallel ADC chip we are going to use is ADC, something like we will go for 0804. Okay, this particular ADC we will use to connect your microcontroller. So what we will do is, input we will connect it. You are able to see notepad?
Yeah.
So we will connect input as some sensor. It can be of any sensor. This is the input to your microcontroller.
Okay.
Okay, but your microcontroller will not be able to detect it. So in between we will be using your ADC chip. Okay, so ADC and microcontroller, or you can use input and then send it to microcontroller, depends on your pin. Okay, now I will have to, okay, I will show you what is the pin diagram used for this particular ADC chip, because as this is an external chip, you will have some particular pins to it. So here this is of 20 pin ADC, whichever we are using. We are using a 20 pin ADC. Okay, just a second, I'll just take a pin diagram of ADC such that it will be easy for me to explain you. So here what you will have is okay, just a second. just a second. I'm just checking out the data sheet if it is available, because whenever you are writing any program for ADCs, you need to have. It's better to go with timing diagram.
Okay.
Okay. What is the timing diagram? I'll show you. When we see timing diagram, it becomes easy for us to write program.
Okay.
That timing diagram we can find it out in data sheet of that particular chip. Okay, that's it, done. ADC. Okay, now if you see this particular, you are able to see this pin?
Yeah.
Pin diagram?
Yes.
Okay, now here, what we have is, see, here this is a 20 pin IC which we will be connecting to your microcontroller to use it for ADC application. Now, first is your CS. CS is chip select pin. Chip select pin here, this is even a bar is there on top of the CS, which indicates that it will become active when you are giving a low value, which means whenever you are giving 0, it will become activated. Okay, so when you activate this chip, then only this particular ADC will work. Okay, that means you need to activate it with ground, or you can say 0.
Okay.
Fine. Next is your read pin. Now, read pin is whenever you receive a signal. Okay. And which is active low. It converts. It will read the input.
Okay.
Okay. We are using it to read the input and convert the data.
Okay.
Without giving a signal to this pin, it will not read the input and convert the data. Okay.
Okay.
Fine. So here what you will have is how much, in how many, you will have something called resolution here. Okay, so that resolution is nothing but number of steps, or you can say with what accuracy it is converting. Okay, now here what you will have is, if you have 8 bits of input, or you can say that you have n bits, or outputs is this much, that means how many bits we will have? 8 bits. 8 bits means 255 values, 256 values, right?
Yeah.
So how it will find out that if you have 256 values, it will have to convert your 0 to 5 volts in 256 steps.
256 steps.
That means, yeah, 256 steps. That means what? Here if you have something like, I have my input as, if my steps are supposed 256, if you have 256, that means what? My input range is from my input of temperature sensor, suppose you have it from 0 to 5 volts. Okay, so here maximum value will be 5 volts.
Yeah.
This is an analog value, so you will have a variable range, you will have some particular voltage ranges. Okay, so I will have a sensor which is working for 0 to 5 volts. Now, how I will convert this value is, I'll divide it with number of steps. 5 volts divided by 256 steps. So I'll get something like somewhere around 19.53 volts I will get. Not 19.53 millivolts, sorry, not 9. So I'll get something like 19.53 millivolts, which means what? If there is a change of 19.3 millivolts in your ADC or in your input, it will change the value.
Okay.
Okay, that means if I am showing 19.53, it is 0 volts. If I'm adding one more 19.53 to it, suppose we assume it like 20 volts, 20 millivolts. That means first, if there is a change of 0 from 0 to 20 millivolts, it will assume it as 1. 40 millivolts 2, 60 millivolts 3 value. Like that, it is converting your 256, or you are converting your 5 volts into these many particular voltage ranges.
Okay.
You understood? No.
Can you explain it again?
This is the smallest change detected.
Okay.
Hello?
Hello. Yeah.
This is the smallest change detected. That means you are able to detect a change which is of 19.5 millivolts.
Okay.
Hello?
Yeah.
So here this is the 19.53 millivolts is the smallest change which we can detect. If you add up this 19.53 millivolts, you will get somewhere around 5 volts. Why we are using 256 is because we need what 8 bits of your we need 8 bits of output. If you have more 10 bits, then you will have somewhere around 2 power 10, which is 1024. Okay, if you have 1024, you will have to divide this 5 volts by 1024. So you will get 4.88.
Okay.
That means it has a capability of detecting the smallest range of your voltage as 4.88. If there is a slightest change which is of 4.88 millivolts, it will detect it.
Okay.
Basically what you are doing is you are dividing your 5 volts in numbers. Okay, so that number I can't have it without voltages, so we will divide it with millivolts. 4.88 millivolts is 1. Next is your, if you have 10 millivolts, 2. 15 millivolts, 3. So you are dividing your 5 volts into numbers you want.
Okay.
Okay, so you can call it as resolution. That means if we are using 8 bits, you are able to detect the slightest change, that is of 19.3 with 19.53 millivolts.
Okay.
Okay, this is clear, right?
Yeah.
Okay, now whenever you have something like whenever you are giving a low signal to your, where is this pic? Whenever you are giving a low signal to your CS pin and then you give a signal to RD, then you will be able to see your output at your D0 to D7, which is, you can see, is like 18th to 11th pin, 11th to 18th pin, you can say,
Okay.
which is DB0 to DB7, which is data bit 0 to data bit 7. Here is your output pins.
Okay.
Okay, now here or you can even in some ICs you call this particular or RD as OE. You can be interchangeably, they can use a name of RD as OE. Okay, OE is nothing but output enable. That means once the conversion is completed, just to make this pin low, because it is given active low, a bar sign on it, which means that output enable the output at output pins.
Okay.
That means send the output.
Okay.
Okay. Next you have some pin like next you have pin of okay, we will see this right pin. Okay, what is this right pin? Right pin is simply start conversion pin. Once you give active low to this pin, it will start the conversion process.
Okay.
Okay.
Yeah.
Hello, is it
Yeah.
okay? You will
Yes.
have something like ADC will give you the side pin gives you a permission to start the conversion. Next you have one more pin called INTR. INTR is end of conversion.
Okay.
Okay, so it's an interrupt which says that conversion completed. Like we have seen some interrupt flags like TF flag for your timers. Then we have seen serial interrupt flag of TI and RI. Like that we have INTR flag which indicates that conversion completed or end of conversion.
Okay.
Okay, then you have something like clock input. Now here you can give, there is two options. One is already internal clock is inbuilt into this. Okay, and other thing is you can connect an external input to it. If you're using if you're using external clock source, you will have to connect it at this particular clock input pin, which is 4th pin. Okay, along with this you will be using one more pin called clock R pin, which is a reference to this clock. Otherwise you can use one internal clock also. Okay, so here if you want to use some external clock, you will have some particular formulas of how much you want to connect, what frequency you want and what is the frequency it can provide. That you will have to check out in data sheet. Generally we use it like F is equal to 1 by 1.1 RC. Okay, so it depends on what frequency we want, but irrespective of all these things, the maximum speed with which it can convert your output is 110 microseconds. This is the maximum speed it is able to give. Okay, which is approximately around 600 kilohertz. You can use internal clocks also for this. Okay, next we have some pins called V input and V plus. What is this V input and V plus? These are the pins where you are going to connect your input sensor.
Okay.
V in, generally we use it for V in if you have some differential things, like you're not going to connect your sensor to ground and you have some differential voltages like -5 to +5 or something like that. At that time you will be connecting it in between V input plus and V input minus. Otherwise simply you will be using some V input pin and the other pin you are connecting it to ground. Okay. And generally we connect this V input minus to ground only. Otherwise if you have some differential inputs, then you will be connecting it to that pin. Next you have analog ground. Here you will have two grounds. One is analog ground and the other is D ground, which is 10th pin, 8th and 10th pin. A ground and D ground, which is analog ground and digital ground. So here there might be some differences in between the ground also. So to remove that interfaces from analog to digital values, they are providing two separate grounds, such that there should be no disturbances from analog to digital or digital to analog.
Okay.
Okay. Next you have something like V reference pin. Now here what is this V reference pin? See, all the sensors are not necessarily having an input of 0 to 5 volts. Suppose you might have an input of 0 to 4 volts. Okay, at that time this value changes 4 by 256 changes.
No. Yeah.
Right, but what is the maximum value we are giving is 5 volts. So at that time, why? Because here we have one pin called V reference, right? VCC or V reference. 20th pin is VCC or V reference pin, right? So V reference pin, by default we are giving it like 5 volts, but that 5 volts V reference is for 0 to 5 volts. When you are connecting, maximum input is your 3 volts or 4 volts, your V reference has to change. Right, but we are not changing it every time like, oh, VCC has to be 5 volts. We are changing it like, let's give VCC 4 volts, 3 volts, 2 volts. So what we will do is we will use something by V reference by 2.
Okay.
Okay, so when you have something like V reference by 2, if your input is 0 to 4 volts, what happens? V reference by 2 becomes 4 by 2. Okay, when you are saying 0 to 5 volts, what should be the reference? 2.5.
Yeah.
2.5 to 5. Like if you say -5 to +5, the reference is 0. 0 to 5 volts and 0 to -5 volts, right?
Yeah.
If you have 10 volts range, you are saying it like I don't have 0 to 10. I'm taking it like 0 to +5 and 0 to -5. 0 is your reference.
Okay.
Like that, if you're saying 0 to 5 volts, 2.5 is your reference voltage. If you say 0 to 4 volts, the reference 5 to 4 volts is your reference voltage.
Okay.
0 to 3, 1.5. Like that. And depending on this, then this will also change. Okay. That means if you have 4 volts, I'll be dividing this 4 by 256.
2.
Okay. I'm not going to divide 5 by 256, but 4 by 256, somewhere around 15 point something, some change you will get. Okay, 15 millivolts something. Right. So here the slightest change of 15 millivolts will be detected.
Okay.
So depending on your voltage and number of steps, it will be changing continuously.
Okay.
That we will have to work out very carefully. Otherwise, we'll get wrong output. Now, the other pin D0 to D7 already we have seen. So this is your ADC chip. Okay.
Okay.
Now we will have to connect it. Already we have seen that we are going to connect to some input and B input plus.
Okay.
Now we will have to give the conditions, like every time what we are doing, activating some registers. Now here, as we are using some external chip, we don't have any particular registers inbuilt, right? Because we don't have inbuilt ADCs. If you go for STM32 or ARM microcontrollers, they will have already inbuilt ADC chips. So we need not connect any external chip, but for 8051 or basic AVR microcontroller, now even in AVR we have ADC, internal ADC. So, but in 8051 we don't have, that's why we are connecting it externally. Okay. Once you do this, once you connect it, again like your registers, you will have initialize, you will have to say start the conversion. Once the conversion is completed, you will have to take the output value. All these things you will have to do, but that we are controlling through all these pins. Okay, so how we are controlling that, if you can see in this diagram. Okay, now here when you give a low to, you can see the CS, right? Once you give a low to high signal, it starts conversion.
Okay.
Once it detects low to high signal, it starts the conversion. CS, chip select. That means what? Chip is not start conversion, sorry. The chip is selected. That means your ADC is going to start working. Next, what you are giving something like we will have to give start conversion. So when your chip select is low, when your chip select value is low, at that time you will have to give right pin a low to high signal. Why? Because it will start conversion only when the chip is selected. Chip is selected when you have CS as 0.
Okay.
So you will have to give a value. You can see in red line that when this CS value is low, at that time they are giving one low to high signal, which is simply dotted as start conversion. Okay. Then once the conversion is completed, your INTR will become low.
Okay.
Or you can say a high to low. That pin will already be high, and when it becomes low, it means that your conversion is completed. Select the data from D0 to D7 pin. Okay. One more signal is missing here, which is read signal. Once your data is out, we will have to give one read signal, like we will have to give a high to low. That means by default, they see one thing, whenever you have a bar or you have one line on which says that it is an active low, that time we will have to initialize, or we will have to assume that it is in high condition, and on becoming low it will get activated. So your RD bar will also be high, and once your data output will come, after that you will have to give a read signal to read this send this data to your microcontroller or any output device.
Okay.
Okay.
Yeah.
This is clear, right?
Yeah.
So now what we'll do is we will write a small program for ADC here, and then we will see.
Okay.
Here you will have one problem. We will have to interface this as well as LCD, or else this on. Okay, for now I'll just print the output at port, and then we will find that we will have to see it at try to anything is okay. Okay, today we will interface some other device with this.
Okay.
So we will have to connect how many pins to our microcontroller? We will have to connect CF pin, or we can say if we give directly a ground to it. If we want, we can ground it. If we want, we can connect it to microcontroller. So for now we will leave it. We will connect read, write and interrupt pin, as well as we will connect D0 to D7. That means we will be connecting 10 pins to your microcontroller.
Yeah.
Okay, we will connect this 10 pins, and we will collect the data at some particular port. In here we will connect it at some port 1. We will collect because left side we have a separate port. Okay, we will change it. Fine. So we will use SBIT to write all these things. SBIT read signal, which we are connecting it at some P3.1, and then you have SBIT read write pin P3.2. INTR. Okay, these 3 pins and one more is port. And then we'll connect some SFR, I will call it, and I'll say it like output SFR ADC underscore output, and I'm connecting it at some port 1, or yeah, port 1. Port 1 address is 0x90. Okay.
Okay.
Next we will have to write our main function now. Now what we said, first of all we will have to initialize your pins. Why? Because it is active low, so by default it's our duty that we will have to make it high, such that when it detects that high to low, it will start the work.
Okay.
Okay, because once you make it low, it will become low because you are giving external signal. That means whenever you want to start the conversion, you will have to give us signals like low to high, low to high, low to high, or high to low.
Okay.
See, once you give a high to low, it will start conversion, it will end off conversion. But again, when you give a value, already if it is in low condition, it will not start. It has to get something like a high to low whenever required. So by default we will take some values, but before that we will have to take one variable to collect the values. So I'll take something like value only, unsigned char value, and next we will write this like we will initialize this port with a high value. So we are saying like we need not actually. Okay, we will not. So here we will take this 3 pins, read pin equal to 1, write pin equal to 1 and INTR equal to 1. Fine. We are making everything high. Now what we will do is, we will write our main function here, I mean logic here, which is something like this. Now first of all, what we need to do, chip select by default we are connecting it to ground, or we are connecting it to CS equal to 0. Okay, so first when it will start conversion, we are using this right pin to start the conversion, right?
Yeah.
And this right pin will work when you give a low to high signal, correct?
Yeah.
Hello, is it audible?
Yes, yes.
Yeah. So here this right pin will work. So by default we are giving CSS low. That means chip is selected continuously. But to start the conversion, we need to give a low to high signal on your right pin. Okay. So we are giving right equal to 0, and then again right equal to, that means once you give this, it will start conversion. Sorry, high, and then we will have to give low. Already chip select is 0, and then you are giving a high to low, low to high, sorry, because already it is 1. So you are giving 0, and then again you are making it like 1. Once you give this small signal, it will start the conversion. Now once it start the conversion, we will have to wait for end of conversion. End of conversion is detected by INTR pin. Your interrupt flag will become high. So here in this case INTR is low, so we will have to wait till it becomes low. So we will write this like, while my INTR is equal to high, stay here only. Okay, so while this condition is true, it will be there in this particular line only. INTR by default is 1, so it will be 1 only. Once it becomes 0, which means end of conversion, it will go to next line. So here what we need to give is enable the output to your output pins, which means you will have to give a read signal RD equal to 0. Okay, here output comes, and then you can collect it from your port, from your output data, which is nothing but okay, from your port, which is your ADC value. We will do one thing, okay, which is your ADC underscore output. So as this is your input, we will make this also as your high. ADC underscore output is equal to 0xFF, because we are making every input, all these are inputs only, so we are making everything high. So here also we'll make this ADC high, and then we will send this to some particular value. And as of now, what we will do is, as we are not using LCD right now, just to check out the values, we will send it to, we are not using port we are using port 1 as well as port 3. We are not using port 2, so we'll just send this value to port 2 equal to value. Fine. And then after this, what you need to do is make read equal to 0. Why? Because read needs a low to high value. No, sorry, read equal to 1. Sorry, a low to high value is required when you want to read a continuous thing. That means high to low, sorry, not high to low. Why? Because here everything is active low, so you will have to make these pins as 1. INTR by default it will become 1 again, but you have to give this write and read signal. Okay, so we are making write also 1 again and read also 1 again. This ends your program. This is your ADC program. So basically you are giving a low to high signal to start the conversion. You are waiting for the conversion. As soon as the conversion is completed, you are giving a signal that send the output, and then collecting the output, making that read pin high again, such that again you can give a low signal to it. Is it clear?
Yeah.
I'm giving our output at port 1.
Okay.
Yeah, 0x90. And our output should be at port 2. These ICs are required only and only when
Okay.
you are using a controller which doesn't have internal ADC with them.
Okay.
If you have an internal ADC with them, then you need not connect it. That depends again on your application, whether you are going to use it or not. So read pin, we have connected it at which pin? Read pin is connected to P1, P3.1. And right pin is connected to P3.2.
3.2.
And INTR is connected to P 3.3. See, rest of the pin I will have to connect a ground. I'll be connecting 2 grounds. One ground is for analog and the other is for digital.
Okay.
And I'm not giving here power is off. See, there is no need to give power here. Why? Because this is a simulation software, but just for reference I am giving. Because even for 805 and IC we are not giving any power supply.
Okay.
The last pin which we need to connect is our input. So basically here we can't use sensor, right? So what we will do is we will take a potentiometer. we will use potentiometer such that we can so here we have different potentiometers, but we will take digital potentiometer. See, here you can see we have digital potentiometer. It will look something different actually. Animated potentiometers will be there. Did you install this software? I mean, is it working perfectly? Did you try it?
Yeah. Yes, yes.
Okay. Variable potentiometer. Okay. What we name here is actually we will have some just if we are able to change this is also okay. We will see this. No, we are not able to change it. It is just for reference. Here you can see that if you have something, if you want to change and if it will not change, it will show you. Okay, okay, we got it. Pot. Sorry, I have written everything. This is an active device. If you have it, then see when it gives you something like active, which means that you will be able to change the value for it.
Okay.
Okay, if you don't have, if you will not be, now just now we have selected something else also, right, which was potential. If you see this variable resistor here, here it is saying that this is the model and this is, but here it is not given whether it is active or low. If you see this, then here you will not be able to change the values directly. Okay, you will have to give one particular value to it, but if you use this, then you need not set the value. Delete this object and I'll just use this one more. So pot, if we select here, so I'll connect the input here. And oh, sorry, I will not be connecting input here. I will have to use this first. I will select this as input, connect this to input and the other pins to ground as well as. I'll connect this ground only and I'll connect it to this voltage. Okay, fine. Now when you load this program, see, if you see this port 2, you're seeing something like 1 and all other pins are 0.
Okay.
Hello?
Yeah. Yes.
Okay. Now if you change this value, that means at low it should become all zeros and at high it should all become 1. Okay. So we will simply change this value. First I am increasing it. If you can see that your port 2 values are continuously changing.
Yep.
And at max it become all high. That means this is the maximum value you can read, all ones. And when you make it again low, I am just decrementing this value. If you are able to see, I am changing the potentiometer value. When you are changing potentiometer value, here also port 2 values are changing. And once you reach here as -0, everything becomes 0.
Okay.
Okay, so this is how you are going to connect external ADC to your, external input to your microcontroller. So here, in place of all these pins, if we connect an LCD here,
Okay.
we will just connect and we will just copy one LCD program and we will just connect an LCD also here. So first we'll just select LCD, 16:2 LCD. Alphanumeric LCD, and then we'll place it here. There is one problem in displaying on LCD now. What is that problem is, whatever output you are seeing is in hexadecimal value. Okay, so to display it on LCD, we will have to convert that into decimal.
Okay.
Okay, so here you have, again you will have to change that. So what we will do is, we will simply write one function or something to convert and then display it.
Okay.
Okay, whatever output we are getting, that will not directly, we will not be able to. We are getting hexadecimal value and your LCD is alphanumeric LCD, which is displaying ASCII values. So we will have to convert your hexadecimal values to ASCII values. Okay, so how to do that? So first of all, we will have to write a function which will do this for us. Okay, and then we will have to call this function again to display it. Okay.
Okay.
So shall I write it down? Okay, I will only write it down, but we will just finish this off and then I'll write it down and I'll explain you, because again or else if we want to do it now only, we will do it now. Anything is okay for me. So what we'll do is, will you try to convert hexadecimal to ASCII first? And then shall we do it? Your wish. Hello.
Hello.
So you will convert or shall I convert once?
Can you try that? Show me that.
Sure, no problem. So first of all, we need to find out what is the logic behind your hexadecimal to your what is it? First we have to find out what is the hexadecimal value to your ASCII value conversion. Okay, so whatever you have, we will have to change that. So what is the difference? First of all, we need to find out. Okay, so what is the difference? If you see, can you find out what is hexadecimal value for A and what is ASCII value? I have given you one program to convert 0 to 255, right? I have given one program to convert your values, if you remember, right? So here what we will do is, see, first of all I have to get that chart. So I'll just get that chart of hexadecimal to, or I'll just get this chart of ASCII table, because Did you try that first of all?
No.
Then you will know that what will be the difference actually. I'm saving the image, just a second. You're able to see the image?
No.
No. Okay, just a second. Now share it with timing diagram. Here you don't have it. ASCII table. So here the name is 250. Just a second, I'm just sharing it with you.
No.
Yeah, I think it is visible.
I'm able to see only the top. Microvision.
Is this now?
No. Still I'm able to see. Yeah. Now I'm able to see. ASCII table.
So here what we need to do is we need to convert this value. Now this is your hexadecimal value and this is our character value. Okay. So if you see here, we need numbers, right?
Yeah.
We need numbers. So here we have 30 to 39, which will display 0 to 9.
Okay.
Okay, and the equivalent value for this in hexadecimal is 48.
Okay.
Okay. Hello?
Yeah.
So here what we have is, here the numbers are 48 to 57 and the equivalent hexadecimal value is from 30 to 39, which will display from 0 to 9. So whatever output we are getting is in hexadecimal value, and if we want to display it in ASCII, we need to have, like, if 0 add 30 to it, you will get hexadecimal value, ASCII value. 1 plus 30, 31. 2 plus 30, 32. Is this okay?
Yeah.
But before that, if you have something like 255, you are not able to see 255. If you convert that 255, you will get some different value. So what we need to do, if you want to display 255, you will have to separate those digits, 2, 5 and 5.
Okay.
Okay. And then 2 plus 30, 32. Okay.
Okay.
You understood what I'm saying? Here what we need to do is, first of all, we need to separate the digit. If it is 3-digit value, we will have to separate those 3 digits and then we will have to display it.
Okay.
Okay. So what we will do is we will write a function, but before that what we will do, we will copy this LCD program here such that we can display it on LCD. So I'll just do previously whatever programs we have written, I'll simply copy that from there. I'll do one thing. Just a second, I'm adding it. LCD. So I'm simply copying this whole function. Okay, we are not using this one. So I'll just copy it till delay function and we'll display it then. This is copy and I'm using it upside such that when we need not declare it again. Okay, but we will have to change the pins because whatever LCD pins are free, we will have to assign those pins. Okay, so first of all I'll remove this and we will have to use this LCD as port 2. Okay, port 2 is 8090 A0, so we will change it to A0 and RS R2 R3 RS RW I'll be connecting it like for port 3 port 3 port 3 as well as port 3. Okay, is this okay? And now what we will do is we will do conversion. So we will write one function for conversion also. So our conversion function be okay, it has only added this. Oh, two main functions will be there now. So I'll just remove this one main function from here. Why? Because I have simply copied it. So this is our initialize function. Here I am writing one more function for conversion. So I'll write it like and conversion. So here we are passing some particular parameter inside this, which we are saying that it has to be unsigned char some value like t, and then we are converting it. So first of all, see conversion here, what we will do is we will take some character, whatever output we are getting, what we'll do is we will divide it by 10. If we do that, what happens? Hello?
Hexadecimal will be converted.
Hello?
Hello, can you hear me?
Yeah, is it audible? Okay,
Yeah.
So now whatever value we are getting, what I'll do is we'll convert it into your whatever value we are getting, we will first divide it by 10 and then we will separate the values. Okay, how we are separating it is, see, if you see this, now if you divide 255 by 10, what happens? What we'll get is
Decimal value.
Sorry. If we divide this 255 by 10, we'll get something like
25.5. Hello.
Right. 25.5, right?
Yeah.
Right. Now, what we will do is, here whatever value we are getting, we will simply use remainders for this. Okay. So, first what I'll do is, we will consider this as remainder. Okay, so first my digit will be something like, if we have 255, we are for finding remainder, what we will use is modulus operation. So first take this modulus and take 255 modulus 10. So what we will get first?
5.
You will get something like, here you will get 25.
5, right?
First you are using, oh sorry, remainder, right? Remainder is 5. And here you will get quotient as 25.
Yes.
Right?
Yep.
Right. Now what we'll do, you take that quotient and then again divide it by or use this what you have 25 modulus 10 again. Now you will get modulus as sorry, already I have deleted it. Okay, 255 modulus 5 you will get, first you will get 5 and then again you will get 5. 255, or not 255 this time, 25. Whatever quotient you have, just to take modulus and again you will get your 5, and then last one is already by default whatever output value you have. Okay, so again if you add this 5 plus 0x30, which is nothing but your equivalent is 48. If you see here in this value, if you see this 48, right? 30 is 48. So when you see this, if you add this, whatever number you get is your what ASCII value. Okay, so basically what I'm doing is we are using the hexadecimal value and we are converting it into decimal and we are adding 30 to it. We are separating. As we want to separate those digits, we are using decimal. I want to separate this 2, 5 and 5. And that's why we are going for this conversion. And then we are simply adding it. So my function will be something like, as I have maximum, my maximum value is 255, right? So what we'll do is we'll take some unsigned char. So here I have some values. So first of all I'll take one digit. So here unsigned char, this is my 3-digit number, so digit 1, digit 2 and digit 3, and then one more digit I'll take it like x. So first what I'll do is take this x and divide this particular t by take this x, divide it by 10. Okay, so we got 255 by 10. Okay. Hello?
Yeah.
You got 25, right? 255 by 10. You got 25. So my digit 3 is 5. So I'll take like D3 is equal to T modulus 10. So X is my quotient and T is my remainder. Sorry. Yeah. Yeah. T is my actual value. So X is equal to T by 10. Here it gives me 25 and here it gives me 5. My quotient is 25 and my remainder is 5. I got my last digit. Okay. Then what I have to do is for digit 2, what I need to do is I need to take quotient from your 25. Remainder. So I'll take it like x is equal to modulus x modulus is 10. So here I'll get my second digit and third digit I'll get it by dividing it. So D1 is equal to x by 10. So here what you will get is D modulus means what you will get 25 modulus 10, you will get 5 and here you are dividing 25 by 10, you will get 2. So we separated 255. Okay. Here my value is 255. So 255 by 10, you will get 25. And here what we are using is 255 modulus 10, you will get 5. Is this clear?
Yeah.
And then what we are doing is we are simply getting this digit. D1, sorry, कौन है अविनाश है? ओके, गायत्री उसमें से दे दो ना, वो 3 में से एंड वो दोनों भी दे दो. Just a second, Kaushik.
Okay.
Hello, Kashi. So here first, what we are doing is we are taking this digit 1 and just add this digit 1 plus 0x30, or you can add 48. Anything is okay. D2 is equal to D2 plus 0x30 and D3 equal to D3 plus 0x30. Here we will do this conversion and then display it on LCD. LCD underscore, you got already data, so here I'll display something like LCD underscore our print function. What is that print function? Print underscore LCD, right? So print underscore LCD you use to display the data. Print underscore LCD digit 1, print underscore LCD digit 2, and print underscore LCD digit 3. Okay.
Okay.
In my main function, what else we have to change is, here we need to change send this ADC output value to your conversion function. So just go to this and write here conversion of this ADC, conversion of this value.
Okay.
So once you go there, your main function will take you to this conversion function. It will convert it and it will print it on LCD.
Okay.
So here we will change this and convert this, and we will connect target not created D1 expected semicolon. I have not written semicolon somewhere. Here I have not written semicolon. Fine. Now we will have to connect this port 2 to D0 to D7 first. Whenever you want to end this session, you just let me know. Why? Because I am free till 11, that's why I am continuing it. But if you are not free, just tell me. Other pins I have connected at to which RSRW enable is at P3.5, 3.6 and 3.7. So this should work perfectly. Let's see what value we are getting, but we are not getting anything. It is not displaying any values, but it is showing that the value is something like 0000 1100. Right. So this might be the this should not be a problem, but somewhere we have missed something in our main program too. We have not initialized our LCD. Sorry, but we will have to initialize our LCD. So our function is for LCD function, because in our main function we have not initialized. Whatever we were using was our different main function. So init underscore LCD is our function. Now we have initialized our LCD. Still we have not given a command for displaying where it should display, but let's see. Okay, now why it is showing all zeros is because we have not given a particular. It is continuously converting your values. Okay, so
Okay.
We know that whenever your LCD is displaying and we are not giving it a particular display location position, it will continuously go on printing, and after some time it will come to next line also. So what we'll do is
Okay.
command underscore LCD, and I'll give here 0x. Here your value will be LCD first function we have said, right? I have said you something like commands, right? So here the command will be something like this. If you remember C0, 8090 commands I have said you. Here we have given some command like C5, right? C4, C5, 80 to display it in first line or second line. So here I'll give command like 0x80 such that it will display it at first 3 positions only. Now if we see this, 000, now increase its value 26. So why it is showing 26 is because precisely I am not we are using this particular digital thing, that's why it is showing us that we are not changing it very slowly.
Okay.
That's why the maximum value should be 255. See.
Okay.
Okay. So
Yeah.
this was about your ADC. And this is how you convert. Basically why you are using conversion is because you are getting hexadecimal value. Now if you want to convert this hexadecimal value, why, again the thing is, now you can ask that why we are converting it into decimal. The thing is, basically if you see this hexadecimal chart directly, if you will convert it into ASCII, you have 255 values here. Sorry, I have taken only one image, which is maximum is 127, but like that you have 255. When you say sorry, a character is 127 only, you have 128 values. But when you say directly, if you will convert this value to character, you will get some different characters. And suppose my output is 126, and I'll directly convert this, what is the difference, whatever is there, to your character, you will get this not symbol. Okay. So, but I don't want to display this 126 as not. What I want to do is I want to display this 126 as, or you can say that particular 7D or 7E value into alphanumeric, which is separate characters 1, 2 and 5, or 1, 2 and 6. So what we are doing is, that's why we are converting it into decimal, separating those digits, and then we are converting it into your character.
Okay.
Then it will display something like, when you directly display 10, it will display line feed. If you see first line, 10th character A, it is line feed. A in hexadecimal is line feed. If you get a 12 in hexadecimal is vertical tab. So like this it will display. But I don't want to display 10. I want to display two numbers, which is 1 and 0.
Okay.
That's why we are dividing it in, we are separating those digits. We are separating 1, we are separating 0. So we will get 1 and 0, and then we are adding 30 to it again to convert back it into ASCII, or you can say hexadecimal. And then we are feeding it to your LCD. Okay. So this is about your ADC. And one more simple topic I'll say, and after that we'll finish it off, such that okay, see, you have something like DC motor, right?
Okay.
DC motor and stepper motors are there. So how this DC motor and stepper motor are working, and here you have something like